Let us look at the practice problem for the midterm 2. So our midterm 2, we will cover chapter 4, continuous distribution, and chapter 5 about multivariate distribution. So you should expect the same kind of test structure. The problems from practice test, more or less, it will be similar, right? And you have one applied problem. So please make sure you have time um, accordingly for each problem, especially for applied problem. Often it'll be easy. You just follow the step closely. You should be able to handle it. So for this practice test of midterm 2, we have about 25 problem. In chapter 4, I prepare 13 problems. In chapter 5, we have 12 problems. 12 problems. So let me just scan through quickly here. 13 for chapter 4, and then chapter 5, we have 12 problems. By 12, which is the last one. So for these problems, I extracted from either the note, lecture notes, the homework, okay? And say, I think it's important to understand all these problems in detail because, say, it is the way to assess how you digest the material in the class. So for chapter 4, let us first look at problem number 1. It tells us that we have a random variable x, have the mean, and the standard deviation is normally distributed. And then we need to calculate the probability 2x plus 3 less than 5 in another case, which is ax subtract x squared less than 1. So you can see here, like, it's just a transformation, right? The first one, you have a linear 2x plus 3, and this you have a quadratic. So you have an x squared here. So with that, you can translate the problem back to x less than 1. So say if you use a TI calculator, and then you can just do a normal CDF, small number to 1 and mean and standard deviation. But another strategy you can also do it for those people who want to look at the z-score perspective by translate it to the z-score, which you need to subtract the mean and divide by standard deviation. So either way, so if you go to z-score track and then you need to process with normal 0, 1. Let's say if you don't want to convert to z-score and you just process with normal mu and standard deviation sigma. A long time ago, when we don't have this kind of powerful calculator, and then we have to convert back to the normal 0, 1 because we will use table to look at the number. Okay. Yeah, same thing for this problem. It's just a quadratic right form, which means you have a x squared here. So you can solve this inequality, right? And then you can get either this direction or this direction. And again, here you can either directly calculate using a normal CDF function from your TI, or you can just translate it to the z-score. And if you do the calculation correctly, you can check this. The results will be 108. So here, like problem 2, the length of time of failure in 100 hours of transistor is random variable y, cumulative CDF given by this. Okay. So there are 5 parts for this problem. Show that we have a CDF, uh, find the 30 percentile value of y, and then find the PDF, find the property, and then find the property that the transistor operate more than 100 hours, given it can operate at most 200 hours. So it's just conditional property. So now let us look at each part problem. So for the first part, to show it's a valid PDF, right? So this is all the thing you need to check. You need to make sure it's non-negative. You need to make sure, you always have the non-decrease style. You have a right continuous for completion, and you also have like the limit when y go to infinity, negative is 0 and positive infinity is 1. So given that, you can see, for the current status of the function we have like here, so we shouldn't have any problem in terms of non-negative, negative, right? It should be all positive. And you can also show that, actually, you can show that basically, like if this relation satisfy easily by just plug in, and you can confirm that. And the right continuous is easy, right? So this function should be right continuous. You can check it, okay? And then say the direction equal to negative infinite, which is 0, right? Which is 0. And positive infinite, which is, this guy will turn to 0. So basically you get a 1. So all the condition satisfied, so which means it is a valid CDF function. For the 30 percentile value, it's nothing else than just the f of y equal 0.3. And you just solve it backward, right? And you get your y value. Here is 0.598. You can check it, okay? And then for the PDF function, it's easy because it's just basically nothing else than just derivative of the CDF, right? This is the way we define the PDF function for continuous random variable. So with that, you can just take a derivative for the part of y greater than or equal 0, and it gives you 2y e to the negative 2 square, negative y square. I'm sorry. And 0 for the rest, right? When y less than 0. So in D, find probability transistor operate at least 200 hours, right? So 200 hours here, which we have to be in Gaussian in unit, right? In unit, because here, like, they say it in 100 hours, right? So the unit here in 100 hours. So basically, like, here would be 2, okay? 2. You need to, make sure the unit consistent with what they provided in the CDF function, right? So basically, this time you need to find probability y greater than or equal to 2, and you can use the PDF function to do that, but a faster track by looking at the backward way, right? Just one subtract to the CDF, and we want to do this strategy because the CDF is already well defined here, right? Well defined here. So you just plug in, and it gives you this result. And then for the conditional probability problem, again, you have to be cautious with unit, right? So you have to translate it to by this probability. And with that, you just use the definition of conditional probability from 1 to 2, which is F2 subtract F1, and 2, F2, right? So it will give you the result. You can calculate up to, till the decimal place, but if you leave it here, it's still fine, okay? It's still fine. So now we will look at problem 4.3. Prove the following results. For a non-negative random variable with a CDF PDF function fxx and a CDF fx, and then prove that you have a relation where you can write the expected value of x under this integral from 0 to infinite, positive infinite, 1 subtract fxx dx. In the second problem, we want to prove that the e of y subtract a square minimize when a equal ey. Okay, so the second problem is a very important result. It just tell us, the ey is the best, basically the best guess, right? The best guess for random variable. It's minimize this the mean square error, right? Mean square error. So here, like, let's first look at the first problem. So one smart way we can do is that we will go from the right side because we have more thing to do, right? So the inside function 1 subtract fx x basically it's just a property x greater than or equal than small x here, and you can also write in the integral form here, okay? And given that, you just rewrite in this fashion, and it will give us the double integral like this, okay? Because the inside here is itself an integral, right? And now you swap the variable. So instead of look at dz dx here, now you look at dx dz, okay? So the domain, you should be able to notice that the domain also change from 0 infinite, x infinite to 0 infinite, 0 z. And because this guy, if you look at the integral inside here, right? Inside here, the fxz had nothing to do with the dx, right? So you can take it out. So basically like this whole here will be just a z, right? The z, the 1 and a z. And which give us this much, right? So it will resolve the first integral, the inside integral here. And with this is nothing else than just the expected value of x, okay? Expected value of x. For the second case, now let us just mu is the ey, okay? So we do a small trick here by plug in the mu and take away the mu. And then with that, we can rewrite this square here in this fashion, okay? And basically this is nothing else than just the sigma square, right? And then this and this you cancel out. It will give you this much, okay? So from here you can see that this quantity will be minimized if this minimized, right? And the minimized value of this will be the A will be equal mu, A equal mu. So basically it just tells us like the mean is the best guess, right? The best guess. If you have a random variable and you want to minimize that, and the mean will be the best guess. Number 4, an insurance company sell an auto insurance policy that cover loss incurred by a policyholder. Subject to deductible of 100. Loss incurred follow exponential with mean 300. So we have exponential distribution with mean 300. Calculate the 95% time of loss that exceed the deductible. And then quartile Q1, Q2, Q3. So basically here we need to care about the case the loss exceed the deductible, right? So it's conditional distribution. Because there's no point to look at something below deductible, right? People won't file a claim if, the damage is less than the deductible. So here, if we denote x is the loss incurred, and we have this fashion, right? If we follow exponential here, because the mean is 300. So the 95% of B, you have to be cautious, right? We're very cautious about this. It had to be this, okay? X greater than 100. So you don't have the less than 100 chunk. It had to chop, it had to be trimmed at 100, right? So this is a very kind of favorite style in P exam, okay? Because they're always deductible in most of the insurance policy. You can get the not deductible, but you need to pay higher premium for sure. But often people, they, go with some deductible to lower their premium. So in this case, it will be calculated by this, right? Because it's conditional probability. And again, this is a smart way to do that by looking at FP subtract F100. It gives you the whole domain here. And then you just plug in by look at the CDF of the exponential, and it gives us this result. And you plug in, you will find that it's about 998.72. And then for the first quartile, second quartile, third quartile, it's just the same, right? That's the same. Basically, you need to find the P, right? Corresponding to the first quantile, which now you have 0.25 equal to the P here. So here in this case, our P will be Q1, right? Q1. So you can find the Q1, a Q2 or Q3, or whatever percentile value, right? So the first, the second, and the third, which is the 25, 50, and 75, just three special case. But actually, for any k percentile value, you can also find it, right? We can make a general formula for this as well. So here the proof that for uniform AB, you can get first is the integral will be 1. Basically, it's just a valid. It makes sure we have valid and PDF. Okay, and here the FY here you should be able to understand that that's just 1 over P subtract A, right? Well, on the support from A to B and 0 otherwise. And proof for the mean, the variance, and the moment threading function. So let's look at the problem proper part. Okay, so here just PDF of the uniform, and for sure you can confirm easily that the integral will be 1. The expected value just the y times the PDF. So at the time you can write this way, and you do some simple calculation. It gives you this just half of a plus b. The variance, we use the formula, the shortcut like y squared subtract ay squared, right? The mean square. So e of y squared subtract ey squared, right? The square of ey, the square, the mean. So it will be this fashion, and then you plug in and you should be able to achieve this result. For this moment threading function, it's just, follow the definition. And again, just some simple plugin, you will get to this. Okay, you can confirm all of those step by step. So the uniform is very nice to work with, right? It's easy. The calculation is simple because basically like it's just a constant, right? You can take it out easily. And I say for the mean or the variance, you just do a little bit labor for integral of a polynomial, right? Polynomial. In 6, the owner of an automobile insurance insures it against damage by person insurance policy deductible again. Deductible here, you see. In the event automobile is damaged, the repair cost can be modeled uniform variable interval 0 to $1,500. Calculate standard deviation insurance payment in the event automobile is damaged. So again, this is a pre-exam problem, and you should be aware again, there are also with some deductible, which means why conditional probability very important. Okay, you have to understand it clearly in order to conquer the big exam well. Okay, so here like let y denote the insurance payment, and then we have the y equal to this much, right? When the x is from this and y equals 0, which means like people won't file claims when the damage less than deductible, right? And which means the company don't need to pay it at all, right? So here we have a constraint because the repair cost here is modeled by 0 to 1,500. So in this case, you can see that EY the expected. So what you need to you want to find that the standard deviation, right? So in order to get the standard deviation, you need to get the mean, and you basically the first and second moment. So just E of y square subtract to the first moment, the EY square, right? So the first moment EY here, you should know that your y will be 0 for this range because the company pay nothing. But for this range, it will be this much, right? This much. So from that, you can get the mean here. And similar for the second moment, again, you have nothing here. I think we have plus here, okay. And then the second chunk, which is this chunk. So you do integral, you should get this much. And then the variance, which is second moment subtract to the first moment square, right? And you get this, and from that you can calculate standard deviation. So it's important to pay very special attention, okay, about the deductible case. And of course, you need to calculate the EY correct, right? It's definitely be correct, but if this wrong, and basically like the whole won't be correct, right? In 4.7 here, uh, for y follow exponential lambda, prove that we have the integral one. So here just again we just confirm it's the valid PDF. Then prove that the CDF in this fashion. So just some integral calculation, right? And prove the mean and the variance and the moment certain function and the memoryless property. So which means if you know up to t, and after that it has nothing to do with the t, right? You just take the s here. Let's say if you that person survive after 180 days, right? What probably we know that, right? 182 days. So that just reduced to probably he survived more than 2 days, right? So here in the case, this is the PDF of the exponential distribution. So lambda, and you can confirm that, right, by doing this integral. For the CDF function, again, this is a simple integral. You can plug it back here and you get this, okay? And make sure, you also need to confirm for the case L of the support, right, to make a completion of the CDF function. And then now, let's see, the expected value, which is the y here. So here, like we have a little bit integral by part here by applying the formula u dv equal uv subtract v du here. So in this case, you know your u is y and dv is this quantity. And from that, you can write in this fashion. Just rewrite integral by part here. But remember, this first chunk here, you need to process a little bit for the case, the upper case, right? When y go to infinite, which is directly plugged in one word. Okay, so sometimes you need to use the L'Hopital rule to make it work. Okay, and then processing the remaining integral. So this guy is you can confirm it's just 1/λ here. And with that, you can find your EY after the integral by part. And similarly, for the EY square, right, you needed to find the variant Y, which is you do integral by part, okay, 2 times, right? One time, and you go down, do another time, and you should be able to get this, all this, evaluation step by step. You can confirm those. And from that, you can get your EY square equal this quantity, and from that you can find the variance. So again, this problem is more or less just an integral per part, right? But for the moment, the first moment you do 1 time, the second moment you do 2 times. So the main point here is just you reduce the y square to nothing, right? To the constant, and then other time you can process the integral. And for moment charting function, and then basically it's just block in here, right? And block in here now it's become to a nice established form here, and which means from that you can get the moment charting function. So basically it will be this, right? And you can rewrite this fashion, okay? But again, this integral has a important property. It will converge, right? When your t less than lambda. So make sure this guy is negative, right? Negative, right? So in this case, your MGF is only work for this domain, okay? For this domain. And for the memoryless property here, you just use the definition of conditional property, which is in this case, right? And then you write out what is the numerator and what is the denominator. So numerator here in this case, it can be reduced to this, right? And with the CDF we already found, you can find directly. You can also look at the track using the CDF. But in any case, after you do that, and it should give you this quantity for denominator and this quantity for the this quantity for the numerator, right? Which is probably y greater than x plus t and y greater than t. And this is just for the denominator, which is probably y greater than t. So it will reduce to this form. And so this we call the memoryless property. Okay, it's a very important property of the exponential distribution. So here, like for problem 8, suppose the number of miles that a particular car can run before a battery wears out is exponential distribution on average of 10,000 miles. Then another car need to take a 5,000-mile trip. Find probability he will be able to complete the trip without having to replace the car battery. Okay. So for this problem, because you did model it by exponential distribution, so basically like this is your lambda, right? It's 1 out of 10,000. So here, like because you did model by exponential, so you should make use of the memoryless property. Okay. So say like we need to find the property that the car won't fail, right? So it still can run up to more than 5,000, even that it only drove k miles, right? So basically, this is a probability you need to find. And because the memoryless property, so basically in this case, it just reduced to this form, okay? And you just plug back to find it very easily. So in here, a computer manufacturer collect data on how long it takes before its computer fail. The time to fail in year follow exponential distribution. 20% of each component fail within 2 years. And the probability of a random selected computer fail before time t in year is 0.8 and calculate t. Okay, so now it's kind of backward calculation. But now let us just unravel the problem, in terms of the formula, and then we see what actually we need to find here, right? So here, like we let beta is the mean of the x, okay? So here they didn't say anything about the mean, right? They just say 20% of each computer fail in 2 years, right? So you can see that because 20% fail in 2 years, which means that 0.2 equals property, just a CDF, right? And with that, and we did know that we model by the exponential, right? So this is basically nothing else than this just a CDF function of exponential. Here, if the beta is the mean, and from that you can find the mean beta, right? Right, mean beta of the exponential. So the exponential can be specified if you can find the mean, right? The beta, right? And then now we know t be the time of 80% fail, right? So basically we have like point A equal probably x less than equal t. And again, because we have exponential, and we did specify our exponential with a mean beta, right? Equal 8.96 to A4. So from that you can find a t, okay? You find a t. So you need to make sure you use all the assumption given to us, right? Most of the time we will need all of them. Sometimes they give us redundant, but most of the time. So this is also one big exam problem. In a certain year, an insurance company profit is modeled by normal distribution with mean 6.72. The 80% of the profit is 8.4. Calculate the 90% tie of the insurance company profit in a year. So we want to find 90 percentile value. The value where probably say x less than equal p90, right? Equal 0.9. So how we do that here? So here, like if you know x, right? The company profit given year, so we can get x follow with the mean. And then we don't have a standard deviation yet, right? But we know that 80 percentile is 8.4, right? So this is a thing it gives us, right? So from that, because you don't have standard deviation, so you need to make it calculate out to specify the x specific, clade, right? You want to find the sigma. So which means because of this, right? So you can translate this to the z-score. So which is z less than this quantity equal 0.8. And for the z-score, now you can find the value, corresponding value to this chunk, right? This chunk. Just the 80 percentile value of this score, which is inward 0.801. So this much will be equal to 8.4 subtract 672 divided by sigma will be equal to 0.84162, and which means like sigma 2. And because sigma 2, now you can find the 90 percentile easily. Okay, so here we translate it to the z score, which is probably z less than 90 percentile, subtract the mean divided by standard deviation we just calculated, equal 0.9. And again, this will be the inward norm of 0.901, which is 128,155, which can give us the percentile, 90 percentile value 9.82 or 28, okay? For 11, a two-part machine function when at least one is part working, both part working today. The future lifetime of each part exponentially distributed will mean 5 years. The lifetime of the part are independent. The machine one function 1 year from now. Calculate the property that both parts will be working at the time. So we have some condition here, right? The machine function 1 year from now. So let us look at the problem in terms of the formula here, okay? So if we didn't know x be the random variable that a part work, okay? So at the time we can see that this is something we have, right? Probably x greater than x be equal to that quantity, because here we model it by the exponential, right? So which means this is probably x less than x will be less than will be equal 1 subtract this quantity. This is just a basic property, the CDF function of the exponential. So we can use it, say, except if we ask you to prove it, right? And then you need to provide the proof. But otherwise, you just use it as a very, common use formula, right? And this is why we allow you to bring one page formula in the exam, right? So from 1 year from now, what probably both parts work, even at least one part work, right? That's the condition they give us here, right? The function, the machine function 1 year from now, which is at least one part work, right? So here, this is probably we want to calculate. So we can translate it to both parts work, at least one part work, right? So part work because each of them independent, right? Independent. So you can see the first work and the second work, right? So the first work, which is e to negative 0.2, the second work also this much, right? So it's just the product. But then at least one part work, which means in the denominator here, and at the other time, an effective way that doing a complement, which you know of them work, right? So none of them work, which is the first one not work, right? Which is fail before 1 year, and the second one fail before 1 year here. So when you plug in, this is the answer. For 12, in a vacation timeshare marketing business, the value of timeshare points is modeled by random variable x. We follow gamma distribution with mean 6 and variance 18. Calculate probability of that the value of timeshare point exceeds 4. Okay, so here in this case, we have a gamma distribution. And for the gamma, we should be able to know that it is property, okay, here, okay, from a mean and variance here, and we model it by gamma 2, 3, okay. And here we calculate the property x greater than 4, so which means nothing else, and we just plug in the 4 to infinite, right? And then this is just the PDF of the gamma function. And then just integral by part, right? Integral by part, and you should be able to get, this. Okay, so this is just integral by part. And then you plug in and it should give you the answer, which is probably x greater than 4, okay? Greater than 4. An insurance company's annual profit is normally distributed between 400, 100 and variance 400. Let Z be normal distributed 0, 1, and F be the cumulative of Z, okay? Determine the probability of company profits in the probability profit in a year is at most 60, okay? So far I brought the profit less than 60, right? Less than equal 60. Even the profit in a year positive, okay? So we know that even profit in a year positive. So this is a conditional probability problem. We have a profit is mean 100, variance is 400, which is standard is 20, right? 20. So sigma 20. So this is a probability we want to find. So again, this is a conditional probability problem. But here, like we look at, they want us to use determine. Okay, so here they want us to represent thing using the f, right? The f here. So if you use the f, which is as a give us, right? So basically, you can translate the x here to the z, right? And which means it will give us the f's -2. So this guy -2, this guy -5, and this is just you can rewrite in this fashion, right? So hey, for the normal, okay, but something you should notice that for normal distribution, you can also have this relation, okay, relation. So with that, so you can rewrite the answer in terms of f like this, okay. If you have the TI, you can also calculate this explicitly, but here like we want to write it in terms of the f, right? The f. So if that's the case, and then this is how you write your probability, okay? F5 subtract F2 and divide by F5, right? F5. So now we're going to move to chapter 5 about multivariate distributions. The first problem here, we have a random variable x and y with a joint PDF given by this fashion. Domain, support domain will be 0 less than x less than y and x plus y less than 2 with a k x square y. So k here not specified yet, right? So there are some 7 questions. Find a k to make a valid PDF. Find a property x plus y less than 1. The marginal PDF and CDF. And check if x and y independent. From here, even with the form of the density here, right? We can see clearly they cannot be independent. But anyway, then verify marginal x follow beta distribution. So that I just come from the part C, right? Part C. And then derive the conditional density y given x. So this is a very comprehensive problem. I would say, if I have to choose one problem, right? This must be the problem for the chapter, right? Because it tells us everything from density to finding property probability, finding the marginal, check independent, derive the conditional density. So let us look at the problem part by part, okay? So first thing first, find K that make a probability density function. So important in a multivariate distribution is that you have to be very clear about where your support domain, okay? So which means you need to visualize somehow, because it will help you to calculate your integral, okay? So when you need to find the K satisfied valid PDF, basically the definition is that we require the double integral for the bivariate case from negative infinite to positive infinite is 1, right? For x and y. But because we have a support constraint, right? So basically it can be shrinken to this. Okay, so after you write it down, you should be able to know that the constraint region we are looking at is that for x from 0 to 1. Okay, this is a 1. And the y just from x to the to subtract to subtract x, right? So this is a constraint domain. So which means like you can rewrite your double integral in a more explicit boundary, right? And this will be 1 to make sure it's a valid PDF, right? So then you just calculate layer by layer. For this guy, the x the inside, the dy layer here, the x squared had nothing to do, right? And the k had nothing to do, so you can take it out. So basically the inside layer you can extract by this. And with that, you just plug in, right? And do another layer, the outside, and you get k by 6 will be your integral. And because that's 1, right? So which is k by equals 6 will satisfy the requirement. Then I find probably x plus y less than 1. So now the constraint even more stringent, right? You want x plus y less than 1, right? So the support previously say x plus y less than equal 2, but now you shrink it down. So at that time, your domain support will be this fashion, okay? This fashion. It will be more stringent. And you can easily find out this intersection will be half, okay? So the intersection of two line, right? X equal 1 minus x, so it give you half. X equal half, and which means y equal half. So with that, this is your new support domain, and you just just the same, right? Your case specified already. So which means in this case you have your x from 0 to half, and your y from x to 1 minus x. Okay, x here to 1 minus x. And the same at above, you can find this will be 132. Okay. For the marginal, when you look at marginal of x, right? So basically, like at that time, you just integral over y, but then again, you also need to pay attention on where your y will be restricted to, right? So this bringing back to the original problem, right? So for the x here, the marginal x, your y will be this, right? From x to 2 minus x. So it gives you the marginal of x, okay? Oh, x belong 0, 1. So which means it gives us this. For a marginal for y, which means marginal for y and with this support region, okay? And there's some additional work we need to look at, right? Because, for your y here, yeah, the domain vary when you integral over x. It's either from this 0 to this, 0 to this, right? So there are two cases. There are cases where y less than 1, which is below here. And other time, your x will vary from 0 to y, okay? And this is in this case, your x vary to 0 to subtract y, right? To subtract y. So which means there are two different cases here. 0 to y for the 0, 1 here, and it gives you this quantity. But for 1 to 2, it will be 0 to 2 subtract y, okay? So you have to be very careful about the domain, and this is why visualize important, okay, important. And from that, you can see that fyy equal to y to the 4 here for this case, and this will be for this case, okay? And with the PDF calculated, right, you can easily find the CNF for each case, okay? You can easily find the CNF for each case, okay? And with the PDF calculated, right, you can easily find the CNF for each case, okay? And with the PDF calculated, right, you can easily find the CNF for each case, okay? And with the PDF calculated, right, you can easily find the CNF for each case, okay? And with the PDF calculated, right, you can easily find the CNF for each case, okay? And make sure you also include the domain outside of the case you calculated, right? Which means 0 before that and 1 after that, right? And for the case for the y, it had to be, we have some extra thing, right? Because you have two cases for the y when 0, 1 and 1, 2. And after 2 or before 0, it's just like normal 0 and 1, right? And then for independent, as said, we can look at it directly from the support. You can tell that, but you also just do the product, right? Fxx times fyy, it cannot be equal to fxy, right? You can check easily. Fxx here, fyy here, right? And if you do the product, there's no way for you to make the marginal back. And then check it, it's a beta 32, right? So you should be able to know that what is the function of beta 32, right? So this is a function. And exactly, it just match with what we got for this calculation. So it's a beta 32. And the conditional density function, right? Which is, which is use formula, right? And you just plug in fxy divided by fxx. So long as you can specify the marginal correctly, and that will be followed naturally, okay? So in problem 5.2 here, we have a joint density. You find the mean, the variance, and the covariance correlation, and then expected value. It's also an important problem, right? Because what we care about when we talk about uncertainty quantification is that the mean, the variance, right? And now we look at the bivariate case. And for sure, if we don't understand the bivariate, there's no way, we can understand any high dimension, 3, 4, p dimension, right? So for Ex, here we have formula x times to the fxy. And remember, right, we have the domain constraint. And given that, right, you can also just the same strategy I said, right? You just draw the picture and you can get the Ex by look at the domain. And same thing, the Ey, you can also do that, right? To the same, okay? But always pay attention about the constraint domain. And the variant of x and variant of y, and then just variant of x, just Ex squared subtract to the mean square, right? Ex. Yeah. Expected value, second moment subtract to the first moment square. And then you find the second moment just the same fashion. And from that, if everything correct, you should be able to get variant x equal this much. The same, you can also find the second moment of y. And then you get the Ey square. And from that, you can get the var x and var y. For part B, which is find the covariance and correlation, right? So covariance is the formula for the covariance. So now the remaining task just find Exy here. So just the same thing. You do integral of xy times the PDF and on the constraint domain, and it gives us 320. And then with that, you can get the correlation by using the relationship. Correlation of xy even covariance equal covariance divided by the square root of x over y. And you plug in everything, right? You get that. For the mean up to x plus 3y, which is the property, you segment it out and you use the result you obtain from A. The variance, it's just we have a result for this as well, right? And you plug in and you get this quantity. So again, yeah, you need to basically more or less for this problem, you need to do the Ex, the Ey, the Ex square, the Ey square, and the E of xy, right? Xy. Exy here. And if everything's calculated correctly, you should be able to plug in to find this value, right? The covariance, the variance, the correlation, right? Or maybe some kind of linear combination. An actuary determines that the annual number of tornadoes in the county P and Q are jointly distributed as follows. Number tornadoes in county Q, county P, and we have a joint PDF, right? So some here must be one here. You check. Calculate the conditional variance, the annual number of tornado in county Q, Even then no tornado in county P, right? So no tornado in county P, so which means here, right? So now you restrict yourself to this much, right? And you want a conditional where annual tornado and county Q, right? So here, like you can see that with no tornado county Q, right? The probability of 0, 1, 2, 3. So you can get it much 12, 25, 6, 25, 5, 25, and 5, 25. So this thing come from basically you just normalize, right? 12, 6, 18, 23, 25, right? So you renormalize this, right? Under the constraint, no 0 here, right? So basically from that, you can get the mean, right? The mean of a 0 tornado, the 1, 2, 3, right? So it's contributed will be, the mean will be 0 plus 6, right? Just 0 times the weight plus 6 plus 1 times the weight plus 2 times the weight and plus 3 times the weight, right? So it gives you this much. So 20. So it's a definition of the mean, right? Xi times Pi, right? So here the Pi, P1, P0, P1, P2, P3, and then Xi will be 0, 1, 2, 3, right? And you can also find the second moment, right? Easily 0 square plus 1 square, 2 square, 4 square, right? And with the second moment specified, right? Then the second moment subtract the mean square, it gives us the variance. So it should be easy here. So again, when we have conditional probability, you need to know, your domain now is string, right? It's string somehow. Prove that for bivariate normal, if you have the correlation is 0, if and only if x and y independent. So two way, right? If your row is 0 and then x and y independent, if x, y independent, then row 0, right? So for the first case, you see that when row 0, right, then x and y independent. And why? Because you can write the density of x, y by this, okay, for multivariate normal. And when your row is 0, and you can write here. So basically, you can segment it, factorize by x and y. Okay, you can rewrite this by fxx, yy here, which means x and y independent. And for the other direction, say if you have two independent, then rho equal 0. So for the correlation rho is defined by here, right? The covariance divided by the sigma x, sigma y. Now we look at the covariance. Okay, so here like, we have something extra here. So probably just think maybe the sigma alpha is 1 also fine. But I mean, anyway, well, the numerator covariance xy, it can be written by this fashion, okay? But because independent, it will give us the exy here. It can be segmented by ex, ey, okay? So the numerator is 0. So which means it doesn't matter what happened in the denominator, right? It will be 0 for the row. So we have this is one very powerful thing with the bivariate, the normal, okay, and the bivariate normal here. So if you can show that row 0, then you can see you have independent. Independent row 0 is correct for all random variable, but for the rejection, if row 0 and independent, it only it hold for bivariate normal, but in general, it doesn't hold, okay. Problem 5.5, consider 6 boxes, 3 boxes have 2 darts, 2 boxes have 4 darts, and 1 box has 5 darts. A player randomly pick a box and shoot all the darts in the box at a target. Suppose we can hit the target probability 0.6. Then you know X is the number of darts in the box he picked, and Y and time he hits the target. Find the Joan PMF of XY. How many times would you expect the player hit the target before he has chosen any boxes? Again, given player has 3 times 5 his probability, and then finally are X and Y independent. So here are two things, right? You choose a box and you throw and you count how many hits, right? So the John PMF of X and Y here, and you can see that, it works by this way, right? So if you pick up block of 3, you pick a ball of 4, you pick a ball of 5, so this is probably you hit, right? Otherwise it'd be 0 here. So it's the way it distributed in such a fashion, okay? It will depend very heavily on which block you choose, right? And then for the secondly, right, the second question, right, for the expected time, number of time he hit again, right, before choosing any box, right. So in this case, you see that the probably he choose the box with 3 darts, which means 3, 6, because we have 3 boxes like that, right? 2, 6 for the 4 darts and 5, 1, 6 for the 5 darts. And also because, when you choose a box with a X dart, right, it's modeled by the number of hits will be modeled by binomial. So which means the mean here in this case would be XP. So given that, you can see that the expected value, which is the marginal case here, you only consider number of hits. So it can be segmented by 3 cases here. You come from 3 darts, 4, 5, right? And you give us, you plug in, you give us these 3, which is the marginal expected value here. And then like in the part C, right? Part C, they ask us how many times would it backside before he show if he hit. So now you know that he hit 3 times, right? So what is the probability distribution of X, right? What probability distribution of X, which is number of dark in box he picks. So say that if you don't know this information, right? So basically like you see you're more likely to pick a box with 3 dark, right? Because we have more of those box, right? 50%. But here the additional information given to us, right? He hit the card 3 times. So for sure, if we make a guess, right? Random guess, what box he actually picked, right? So it shouldn't be the box with 3 dots, right? Because he hit the target probably is just 0.6 here. So it must shift, right? It must shift somehow. So if we don't have this condition, and if you ask, I ask you make a random choice and make what box he just pick, and probably the best guess will place on this guy. But here the additional information I have, so I will unlikely to make this choice, right? I mean, if I am a wise man, I will have more chance to look at other case. So here you see that for the C, right? We know that he hit 3 times. So which means it can be from box 1 or 2, 3 dots, 3 dots, 4, 5 dots, right? So basically in this case, yeah, again, you can calculate this probability. What if from this happened from 3 box with 3 dots, right? With 4 with 5, right? And this is the probability, okay? The probability Y, the probability you hit the target three times. So it comes from either you choose box 3, box 4, box 5, right? And then like the conditional probability given Y equal 3, you can see that Px equal 3 given Y equal 3 will be P33 divided by Py equal 3. So which is 317. X equal 4, you can also do the same thing, which is basically just the second segment here, right? Divided by the summation. So you get this, and then the third segment divide. So now you can see that thing gets shifted, right? Originally, the probably you choose the top 3 dots will be only we have, and then 2, 6, and 1, 6, right? But now it become like this 3, 17, 4, 17, and 10, 17. So which means you see like if I have to choose a pet, right? And then a bet and make a bet, right? I should bet that he probably picked the box of 5 cards, right? And with that, our conditional problem expected value of X can also be calculated by this, right? So as long after you can specify the distribution of number of dots he picked, right? In the box he picked, right? In the box he picked, given that Y equal 3, and you can also find the EX here. So here, in this case, we are check whether X and Y independent or not, right? And of course here it shouldn't be, right? Because the probability hit the target depends very much on how many um, the X is the number of dart in the box, and the Y number of hit the target, right? So the Y depends very much on X. So if you have more, the bigger X is, the Y will get bigger, right? So here the Y follow binorm of XP. In 5.6, X denote number minus surgery, Y major surgery, and we have a joint CDF like this. For some non-negative integer, X and Y, calculate the probability of the policyholder experience exactly 3 minor surgery and 3 major surgery this decade, right? So we talk about this decade for each of them. So in this case, you can see that this is the probability we want, right? And given to us is the fxy. But remember, we are working with integer. It has nothing to do with continuous here, right? In a discrete case. So you can write in this fashion, okay? You can check it. But basically, this thing you can rewrite, okay? And with that, you just plug in your function, and you can get this probability exactly 3 and 3. Yeah, okay. Let fxy equal this PDF show a value. Okay, so it's for marginal xy independent by the f of those the cumulative distribution, right? Function for each specific value, and the general form. So this problem, yeah, more or less, it just fall back to the same initial problem we work on, right? But now we don't need to validate. We don't need to find the k, but instead we show it's valid shown PDF, right? So basically, again, you need to draw the support domain. Okay, it's important because it will help you to get the correct boundary and for the calculation, right? And here in this case, you check a valid join PDF by make sure it's non-negative and the integral is 1, right? And non-negative is easy because the domain here has nothing to do with negative number. And then the integral now again after you can specify your support region, which is the shaded region here, you can translate easily to double integral with a boundary, and you can find it E1. So for the marginal, again, just the same, right? The same. But this case, it's kind of easier like previously we have in phi 1. So you can also find the fxx, fy, and then from that you can get the marginal. For part C, you can see that it's not independent, right? But of course, if you look at just the support, you also see that they shouldn't be separate, right? They depend each other. And then find those thing value here. So basically, in this case, you have to be very clear, right? Where the domain, right? By look at the intersection. So basically, like here, just from negative maybe infinite to -2 for x, negative infinite to -3 for y. So you have a rectangular, okay? And you look at whether it had any intersection with the support or not. So for these cases, if you draw the rectangular for the support region, okay, for these 3 cases, it had nothing to do, okay, with the support region. So which means it's all equal to 0. And for this case, if you give it 1, because it does include the whole support region, okay. And for each cases here, okay, you also draw maybe this is the rectangular from 0 to 0.2, from 0 to 0.3, right? Negative 2.2, negative 0.3, but we can, because we don't care about the negative 1, so you can think it's just a rectangular from 0 to 0.2 and 0 to 0.3. And you look at that and where it intersect with the support region here, right? And then from that, you can also specialize your boundary correspondingly. And you also get your double integral boundary correct, and which will help you to calculate correctly. Okay. So visually very powerful thing, and I would recommend use it. Okay, use it to avoid any mistake in terms of specify the domain. And then from that, you can also look at the general A and B here. for different cases, right? And you can get it too. And the minimum force required to break a particular type cable is normally distributed between 12,432 and 725 random sample 400 cables in which type selected. Then calculate at least for 349 unit break, right? So here, like it just we care about will not break, right? Under the force this much. So what the probability of success probability here, right? Success here, like we say, will not break under for at 12,400. So this can be calculated by based on the break-in distribution here, right? And then from that you can use that probability to and the binomial distribution because you look at 400, right? So each cable will be either break or not break. So with that, your you can see that your probability y greater than this much will be equal to this, which is 0.9, okay? And then the number of cable n that not break had binomial of 0.9, okay? And basically, like because in your P exam, you're not allowed to use TI-84, I think TI-30. Last time we talked about that in class, right? And then basically, like you need to translate it, the binomial here. So in our class, you just do binomial distribution with success probability 0.9 here. But in your P exam room, you need to translate it a little bit. Here, just the say the correction, continuity correction here. Okay, so instead of looking for 349, you look at 348.5, and subtract the mean here, divide by standard. I think divide by standard deviation, right? And it gives us like 0.97. So your TI-30 in your exam room, it can process with the normal CDF, okay? But it cannot do for the binomial distribution. So this is why this approximation is needed, okay? But for our test, in math for 130, we don't need to worry about that. But it's just a warning, okay? Okay, 5.9. Prove that if x and y independent, then covariance is 0, but reverse is generally not true. So this is pretty much similar with a bivariate normal distribution we looked at before, right? So in the bivariate case, we have the two ways relationship, right? I think it's the problem 5.4 here, right? But for generally, you don't have that. You only have like if independent, you have pro 0. Okay, so you can see that in this proof, right? When independent, we didn't touch any normal here, right? We just look at the covariance. So basically, we already got one side proof from 5.4 already, right? So now what we need to look at is why the other direction not true, right? Not correct, right? In general, not true. So in this case, you can see that an effective way to do that, just give a counter example, okay? So say like here, we consider x is random variable, which we see either -1 or 1. We probably have. Just like toss a coin, right? -1 head, 1 tail, right? Then y random variable such that y equals 0 if x equals -1. Okay, so when you know that x equals -1, then y will be 0. And y will be, when x equals 1, then again, y will be either -1 or 1. We probably have, okay? So in this case, we can see that x and y are highly dependent, right? Because even no x, I know y, right? It's in here, like in the backward direction. The mistake here. So from that, now we just calculate the covariance and see what happened, right? So ex will be 0, obvious, right? X times px, right? X times pi. Ey also 0, you can check it. Okay. And exy, so it corresponding to these cases, right? X -1, y 0, or x1, y1, x1, y negative 1. So you plug in xy here, you see with all the way distributed like that, you get 0. So in this case, you see clearly covariance is 0. But they dependent, right? They dependent. So which means like the other direction not true, right? And in general, it's the bivariate. The beauty is that it's beautiful because you can get that hold, right? So to prove independent, you just need to calculate covariance for the bivariate normal case and show that it's 0. In 510, an insurance company will cover loss incurred or tornado single calendar year, but at most like 3 tornadoes per year. Let X denote the number of tornadoes that result at least 50 million in losses, and Y total number of tornadoes, the joint BDF given by this. So look like continuous sign, but actually it's not, right? Because here we consider number of tornadoes. So again, it comes back to discrete case. Current expected number of tornadoes as a result less than 50 million in losses. So here just y subtract x, right? Y subtract x, expected value. So here like just a possible event here, x and y here, total and then less than 50 million loss, right? Yeah, more than 50 million loss. So what we want is that first thing first, right? You have the C, you need to specify the C to make your distribution explicitly, right? And in order to find the C, you need to plug in, right? And in this case, the summation for all the weight here will be 50, which is C 150. And then what you need to do is to find y subtract x, right? And with that, you just plug in domain here, and it should give you about 1.1, okay? If you calculate correctly. And here is the domain you need to care about. 11. Number of insurance claims per month for the Poisson lambda, YI, USD amount is claim. And the model YI follow exponential with mean mu, and assume that Y1 to Yn independent, and T total amount find ET in variance T. So this is a conditional, right? Conditional thing. You sum over random variable n. Okay. So two randomness here, right? The first random comes from the yi. We follow exponential, and the second random comes from the index, right? N. So this case, you define et, right? And then just plug in there, right? And then like again, you can see the weight here, but it's the n here, okay? So the n can be from 1 to infinite, right? In which you can plug in by this fashion. And with that, you just replace the formula, okay? And by the formula, and it should give you the quantity you want, okay? Quantity you want. So here, like just a property of n equal I. So this is the Poisson, right? The model Poisson. And then for each, right? When the I know, right? And you calculate E, Y, J here, so it's just basically just the mu I, right? Because each of them will be I, right? Each of them will be mu, right? For the mean, the independent, right? And you have I of them, so which is mu I here. And from that, you can also calculate the variance, so the same spirit, okay? So which means in this case, just expected plus the variance here. So this a law of total variance, right? And from that, you can find the variance by this fashion, right? When you fix the n, your life easy. Just find the variance of the exponential. And then from that, you can also, after you Get that, right? You can unravel and bring it to this, right? And then the same thing. So this you can get the expected value of the variance. And then again, the same thing, right? You have an n mu here, and then you can find the variance here, variance n, and it just give you mu square lambda again. Just the same here, okay? So here, in this case, the boson, right? Give you a lambda. And here, just the variance of the exponential, give you the mu square. And here, like, just the expected value of the exponential, get you the mu. And the variance is give you mu square lambda, okay? So from that, you can calculate the variance t. In 12, consider the joint PDF here for the conditional expected value, right, of y given x and variance y given x. So in order to do that, right, you need to know what is the conditional distribution of x, right, in order to find the ey given x, right. So with that, you see that the marginal you can find easily. And with that, you can find this, it will be conditional probability. Okay, conditional probability. So the marginal, the joint divided by the marginal, right? And it can give you this much, right? This much. So it really depends on x here. And say if you remove the small x here, it should give you the general case. So basically, this guy, it will be a random variable, and it's driven by the way how it's x distributed, okay? And here we just look at special case x equals small x here, okay? And the same thing, you can also find the variant of y equal x equal x here. So this guy will be a distribution, and distributed, the way distributed, its weight will driven by the x, okay? How x distribute. But to make our life simple, we just fix x equals small x and see what happened, right? And then other time you just use the second moment, subtract to the mean square, right? Mean and you squared. So the mean here and you squared, you already got it here, right? So the second moment you can got it here by just follow the same fashion. Y squared times the conditional property density function. And from that you can also get the variable y given x. So that's it. Try to digest this thing carefully, and this will be very useful for when you move along with the uncertainty work, okay, and try to quantify that. Thank you for your attention.